Hello. Hi, everybody. Hello. How are you doing? Anything amazing this week? Yeah? What? Eat all the good tropical fruit for me, please. All right. Hawaii, that sounds pretty good. Anybody got tops for that? Yeah? You're going skiing an hour after this? Wow, okay. Enjoy. Unfortunately, it's probably Big Bear, huh? No, it's Mammoth. Oh, it's Mammoth. Okay, at least that's a little good. Sorry, I'm a skiing snob. I did grow up in Colorado. So, nice. Okay, so good stuff is happening this week, right? You know what else is happening this week? What's happening this week is that there are a whole ton of demo notebooks for lectures 10, 11, 12, which are really 11, 12, and 13 because I'm slow. You should definitely be in these. Because I am so slow on the lecture, I'm not going to have as much time as I want to go over these notebooks in class. So please explore these on your own, okay? Largely speaking, these are set up to introduce all the topics that we really care about in machine learning. Measuring, how we're going to do things like model selection procedurally, seeing what models are best. You're going to want to get familiar with these notebooks. They're going to help you with the assignments, obviously. Okay? So make sure you're in here. Hopefully I've got some time today to do a little bit of notebooking. All right. Just to remind you of some critical stuff before we finish off metrics. We have two kinds of sets of measurements that we often use confusing names for. Precision and recall kind of are a pair. Precision measures, as it says here, how many of the items you select as positive class are actually relevant, are actually positive class. Okay? Of the items that you selected, how many of them are actually relevant, are actually positive class? So the normalization in the first case is against what you selected from your classifier. And in the second one, the normalization is versus what are the true positive class labels. Okay. Another pair is sensitivity specificity. Okay. How many of the relevant items are selected? Hey, sensitivity and recall are exactly the same thing. They're just different names. Okay? They're just different names for the same thing. The normalization is how many things are truly positive. The numerator is how many you selected as positive. Specificity is how many of the negatively selected elements are truly negative. Right? So specificity and sensitivity are a little bit more clear as inverses of each other. But this one is about, again, the normalization is what you selected, or the normalization is what you really think is true. Okay, why did I do that? It's because we need to get you through all this. I want the selector. Okay, so this is where we left off previously. So when we were talking last time about true positive rates and false positive rates, something that I did not note for you. So true positive rate is the same thing as sensitivity. false positive rate is 1 minus specificity. Ooh, okay. Right, remember that stupid Wikipedia page I told you about precision and recall will be your best friend? God, this is the stuff why, right? It's so confusing. These are all just different ways of looking at the same thing. But looking at, right, if you're very specific to the negative class, then you're not going to have any false positives. If your specificity is high, you're going to have a low false positive rate. Okay? You're not going to call any things that are actually negative as a positive class. That's what a false positive is. Okay, so when we look at comparing models, we are going to use, at various times, all of these metrics. Why would we use one or the other? Well, what are we caring about? In cancer detection, which of these two models would be a better thing? Right? Let's look at these two models for a second. These two models, one of them is the one we looked at last time. It's got 75% of cases that are actually cancerous, right, are detected as cancerous. So there are 40 sick people. We got 30 of them get predicted as cancer patients, and 10 don't. Okay, our false positive rate is 17% because these people are actually healthy, this entire row, and 10 of them got predicted as cancerous. Okay, so we're in the business of predicting cancer from some sort of measurements from the patient. True positive rate, 75%, false positive rate, 17%. Or we can have a different system that's 63% true positive rate, but only a 2% false positive rate. Which one do you prefer for predicting cancer, and why? Yeah?
I prefer the top one because if I have cancer, it's more important that I know that compared to...
Exactly, right? So any kinds of false negatives or things that are positive class that we don't label as positive class, right? Any false negative result is a bad one for a cancer patient. They don't get treated fast enough. Okay, but what's the trade-off? Like a 17% false positive rate in a test? What's that going to look like? How many people are we going to get that are healthy that are told that they are actually cancerous? A lot, right? If most people are healthy, which is true of the population in general, a 17% false positive rate does imply that not just are the majority of people who get flagged as cancerous healthy, but a vast majority, right? Because like 99% of people are healthy. So 99% of people times 17% get told they are cancerous, and they're not. Whereas 1% of people, if 1% of people have cancer, then 1% of people times 75%, so 0.75% of people get told that they are cancerous properly. So almost every single cancer diagnosis from this machine learning system is actually a healthy person. Isn't that crazy? But that's the trade-off, right? We have to make those trade-offs on our systems. Now, it'd be nice to have this low false positive rate and this high true positive rate, but that's oftentimes not possible. It is usually a direct conflict. When you can lower false positives, you will usually be increasing false negatives. And we'll see why. Okay, so obviously what you'd really like is a system maybe in cancer detection that looks a little bit more like this. Maybe we would accept a really high false positive rate as long as we could make sure that we didn't lose any cancer patients between the cracks. Okay. Now, let's examine why I said that there is oftentimes a trade-off between false positives and false negatives. So imagine our logistic regression system, right? So just a reminder, in logistic regression, we have some sort of decision boundary, and if we've got a data point, then what we're going to do is we're going to turn that perpendicular distance, which could be a number anywhere between minus infinity and plus infinity, and we're going to turn it into a probability of what class we are, right? We do that through the logistic equation. So we take distances here that go anywhere between minus infinity and plus infinity, and we squish them between 0 and 1 into a probability of being positive class. Now, the probability is used to put the decision boundary in the right place. That's our loss function, that probability, that logistic, right? So let's ignore that for a second, because what we really do is we say, hey, anybody whose probability is just over 0.5, you're a positive class instance. And anybody whose probability is just under 0.5, you're a negative class instance. Even though we have these probabilities, we're making predictions in an all or nothing way. Okay? Well, what would happen if we didn't use that 0.5 threshold? What if we used instead, 0.75? Well, I'm going to drop that down here. Oh, we're not going to get any false positives in this data set. No false positives, right? Everybody down here who's negative class is absolutely properly thing. Okay, but oops, we get some false negatives. Those are people over here that are actually positive class, right? But they're going to be called negative class because they're on the wrong side of the decision boundary now. Okay, well, that's really annoying. What if I draw my threshold at not 0.5 or 0.75, but I guess, shit, I got to go even lower. It's probably going to be like here. Okay, so like 0.2. Okay. Drawing my threshold at like 0.2, I now have no false negatives. None of these are misclassified. But I got a lot of false positives. Yeah. Sorry, could you say that louder?
I'm a little confused. What does the decision boundary actually look like? Is it like the horizontal line or the vertical or?
Well, the decision boundary, right? Remember that the decision boundary is going to be a line where the wx plus b plane intersects the sigmoid, right? Now, we have, like, mathematically, what we keep doing is the logistic function of wx plus b greater than 0.5, right? So I don't have to use 0.5 mathematically. I can try 0.75, I can try 0.2, whatever I want as that threshold. Okay? Does that make sense? Okay. So the decision boundary, like if this is confusing, right? I'm just saying that these are negative class examples that lie this far away from the decision boundary, right? So these are all negative class examples that live over here, okay? And positive class examples that live over here that have different distances, okay? But remember, the Wx plus b, that's defining the decision boundary. But by changing this threshold, I'm leaving the boundary in place, but I'm changing what my decision is, okay? So, but by doing this, I can show you that trade-off between false positives and false negatives, right? That's the key of what I'm trying to show you. This is a choice you can make. You can set your decision boundary and then change your decision criteria is what I'm showing you. The Wx plus b stays where it's at because the W is what minimized the logistic function, the log loss. Not the logistic function, I said that wrong. The log loss, which is based on the logistic function, but it is something else, right? Minimizing the log loss set where our decision boundary is. But we can change, hey, I'm trying to do cancer patients. I need to have no false negatives. Okay, so instead of making my decision where it's optimal for the log loss, I can change my threshold, my logic greater than this stuff here, and I can make my threshold this one, right? I can use 0.2, which means I don't lose any cancer patients. Because if my threshold had been 0.5, then I would have lost that cancer patient and never told them that they were cancerous. Okay? But that trade-off means I've got a lot more healthies that are told they're cancerous. Okay. So does anybody got any other questions about this trade-off between false positives and false negatives? Yeah?
Sorry, I'm a little lost here.
Yeah?
When you said false positive, false negative graph, you can see like, does the x-axis and y-axis have something to do?
Yes, it does. That graph.
Is like one of them is like prediction of a label and the one is the other one is true label, or you just use them?
Are you talking about my plus and minus diagram, or are you talking about the one on the left?
Yeah, I can't.
You're not getting the plus minus diagram. This guy. Okay. So again, what's happening here? I used this last time. I used something very similar. So this axis is distance from the decision boundary. This is on the positive side, right? So these are data points that lie far away over here, right? It's like a data point over here, far away from the decision boundary. And this one is a data point like over here, which is close to the decision boundary. Okay? So likewise, these are negative class instances. And if we draw the decision boundary where we normally do at 0.5, right, then we've got one false positive and one false negative. Right? Because if I draw my decision boundary right here, then this guy's on the wrong side of it, and so is this one. Now, instead of drawing my decision boundary right at 0.5, I can change this threshold. Okay? And I can say, yeah, okay, just leave this decision boundary where it is, but instead of only taking, just over the line back and forth, I'm going to have an effective different decision boundary at 0.75 or at 0.25. Okay? All right. So this trade-off between false positives and false negatives. Any other questions? Because it's pretty important. Yeah.
Would there be a situation where you want the threshold to be less than 0.5?
So less than 0.5?
Yes.
Yeah, because that's this one that I've got drawn currently right here, right? So this is, the threshold is at 0.2 because I need to lower it that far to keep this one on the right side on the as a positive class instance and not a false negative. Yeah. Yeah.
Will there be any instances where you want instead of false positive instead of false negative?
Yeah.
Not like
So some other instance, right? Like, what if what you're doing is you're dealing with trying to predict machine failure in an assembly line. And when you predict an imminent failure, you've got to stop an assembly line and lose millions of dollars a day. Well, it's probably X% cheaper to stop the assembly line before it breaks. So if you can accurately predict that, you probably want to do that. But if you're not sure that it's about to break, the loss of having the assembly line might be quite extreme. And this is just, I made it up off the top of my head. I don't know. You can probably come up with better examples. But yes, there'll be times when it's false positives that are bad that you want to avoid. Okay. Good? Any other questions? All right, so if we've got this concept, now we are ready to introduce one of the most confusing metrics to new students, the ROCOC. Okay. Receiver operating characteristics area under the curve, ROCOC. Let's start with just, before we get to the area under the curve part, let's talk about the rock. So, no, not that rock. Receiver operating characteristics. This is an electrical engineering concept from like the 1920s, where we got like radio engineers, and they're trying to distinguish, did we hear the signal? Is it a real signal that we heard over the radio, or was it just static that sounded like a signal? And we're changing the threshold on our criteria for detecting a radio signal. Just like we're changing this threshold here, right? Is it really a signal or not a signal? Okay. So as we move this threshold back and forth on logistic regression, we've already seen we're going to get a trade-off between false negatives and false positives. So as I move that threshold back and forth, when I've got the threshold jammed all the way over here, I know I absolutely have no false negatives, right? This is where my threshold is. If I had this line, which is essentially the threshold is 0, roughly speaking. And if I have the threshold, roughly speaking, at 1, so that my line of decision is over here, I know I have no false positives. Okay? This curve, this blue curve, is what happens with true positive rate and false positive rate as I go from one end of the threshold to the other. Okay? As I sweep threshold from 0 to 1, I'm going to have changing true positive and false positives rates that are drawn out by this curve. Over here, I have no false positives. Okay? That's when my threshold's over here. Over here, I have no false negatives. My true positive rate is perfect. So that's when I'm over here. Sorry, no, I got that totally backwards. You guys should tell me that. Right? So this is perfect true positive rate. Lots of false positives. This is perfect false negative rate. Lots of false negatives. Man. So you see, it's still confusing after all these years. But the important part is that as you sweep that threshold back and forth, you define this curve. And just a reminder, false positive rate is also, God, I can't even frickin' write, specificity. And this is the same thing as sensitivity. Okay? Now, a great model, a really good model, basically has almost no problem with false positives until you change the threshold so dramatically that you get basically no false negatives. Okay? Like a really good model is basically making really good decisions about false positives all the way up until you kind of go over the waterfall and then you really screw up, right? A great model is essentially making a 90-degree corner up here. Okay? We can just change the threshold and we get almost no problems with false negatives, and we still have almost no problems with false positives right here at this zone, right? If you have your threshold right here, we have very little problems either way, false positives or false negatives. Okay. If your model looks like this, it's a pretty harsh trade-off. And the instant that we are getting fewer false negatives, we're getting better here with false negatives as we go up, we're also getting lots of false positives. This line is chance performance. If you have two classes and they're exactly the same frequency in the population, and you're just guessing at random, your ROC curve is going to be right there on the diagonal. Okay. So a ROC curve is a visual diagnosis. Once you get used to it, what it's telling you is things that look a lot more like the blue curve, there is a threshold you can find that's going to give you basically the best of both worlds. Very few false positives, very few false negatives. If your ROC curve looks like the green one, or God forbid, the diagonal line, you know this is a crap model. And yeah, you can choose one. You can get it better on one side, but you're going to have a terrible time on the other side. Okay? Most models look a little bit more like this, right? Where you're just going to have to pick your poison. It's not unusable. You can find a zone where there's less impact on one of these things and not terrible impact on the other. Okay? But looking at the ROC curve of a classifier tells you, is there a good threshold that really gets me everything? Or am I in trouble and I'm going to have to pick just one of false positives or one of false negatives to keep in good shape? Make sense? Okay. Okay. What about the area under the ROC curve? Well, so the area underneath this chance performance diagonal is 1/2, 0.5. It's half of the square, which would be area 1. Okay? A perfect model is going to have area really close to 1, area under the curve. Okay? So ROC, like looking at the curve, that's a visual diagnosis. ROC-OC, area under the curve, is a single number people like to report as like I said, like a measure baiter sort of thing. Like, this is my one metric that tells me my best model. And it's throwing away a lot of interesting and useful info. But if you need to have one metric, you want a ROC-OC close to 1. You want a ROC-OC well above 0.5. Questions? Okay. So the same way you can make ROC curves. Oh, sorry, I forgot I have a cool demo, right? Okay. Another way please work? Oh, good, it is working. Okay, another way to conceptualize the thing is not the threshold situation I was showing you, but how separable is positive class and negative class. Okay, so if your classifier stays constant, the same threshold, but we make the problem easier or harder, you can see the same things in the ROC-OC. Okay? So when your classes are well separated so that you can just draw a line that perfectly separates them, you'll see that the ROC curve goes up to that perfect top left corner. Okay? But when the classes are basically inseparable, that's when you drop down to chance level. Okay? So this is a picture for a fixed threshold and changing problem.
So the separating classes between the positives and negatives wouldn't affect each other that much?
Yeah, like
The area with the curve would be installed.
exactly. So if you're like your dots for positive class were over here and your dots for negative class were over here and there was no overlap between them and you could pick an easy divider line between them, that's going to be your top left situation. Okay? Yeah.
So far, we only talked about like using the raw curve for binary classification. Do we expand this for multi-class?
Oh, yeah, that's a good question. So it's extensible easily for unbalanced binary class. Can we extend this for multi-class classification? Not except on a pairwise basis. So you can do a binary ROC-OC for every pair of classes and then have an averaged statistic. I cannot remember anybody talking to me about an inherently multi-class ROC-OC. But it's a good question, and you should do some more research and prove me wrong. Yeah.
So one thing I was noticing with the model you had on there is there reaches a certain point where the progression towards one on your as an aux score slows down. And I guess that's because of you have less intermingling, so the amount of data points that are being separated from each other aren't as the magnitude's not the same. So the slope change is slower. But does that also mean that at a certain point there really is no need to optimize anything any further because the difference would be so minute?
Confusing the metric for the thing you care about. So you're absolutely right that the metric changes dramatically in the beginning for small movement of the separation and then slows down because of that, that overlap. The sampling gets really sparse on the low probability stuff, right? But do those couple of points matter to you is maybe a different question than, yeah. Yeah, this is my thing in COGS 108. Everything is a proxy for what you care about. Measurements are proxies for what you care about. They're not perfect measurements of the thing. They're just different lenses. And sometimes the quality of your metric matches what you care about, and sometimes it doesn't. So, all right. So you have the two equivalent viewpoints, right? You can move the threshold back and forth with a fixed separation between the classes, or you can move the classes back and forth and keep the threshold the same. And either one will draw you a ROC curve, okay? So the bottom half that I now have started animating is the moving threshold, right? Fixed class separation moving threshold will also draw you a ROC curve, like we were talking about in the beginning. So, also, I just really want to call out Elvira Swalen, who I've never met, but made this frickin' awesome animation that I could steal. because this was so much harder to talk about without this animation. And there's a GitHub repo, if you click on that link, that you can see how you generate these animations and also make measurements with, obviously, you can just ask scikit-learn to make these measurements for you. And if you go look at my demo notebooks repo that I called out in the beginning, that's what's there, okay? But if you want to understand a little bit more deeply about how to calculate this, go check out Alvira's repo. Okay. So just to make your life even more confusing, but I'm not going to bang on this, the same way we have sensitivity specificity makes a ROC curve, there's precision recall curves. I don't see these used as commonly in machine learning, but they do exist. A precision recall curve is similar in that we can distinguish perfection from the chance performance level, but perfection in the case of precision recall looks like this corner, and chance level looks like a straight line at 0.5. So again, your visual inspection of a curve, of a precision recall curve, same concept. As I move the threshold back and forth, I'm going to move right from doing perfect at precision and not so good at recall. And then at a certain point, I'm going to fall off over this way and do better and better at recall as I get worse and worse at precision. Okay? So again, chance performance, perfect performance, realistic performance. You never see an area under the curve on precision recall. I don't know why. Right? It's just like either look at the graph or do nothing. You just don't see that. So now it might be maybe relevant to take a look at the actual curve here. I can't even remember. I think I stole this from scikit-learn's docs. Okay? But note that what's going on here is that the blue recall curve is an unregularized logistic regression. And the orange curve is a regularized logistic regression. Regularization, of course, helps prevent overfitting, right? We're squishing the weight vector with, in this case, an L2 norm squishing the weight vector. So for the same problem, your precision recall curve, blue unregularized, orange regularized. The orange is a little closer, but not a lot closer, to the ideal curve, right? It's a little bit further towards that top right. And that's typical. That's the kind of thing you're going to see on realistic problems, is small improvements with a regularization term. Anybody got questions on this stuff? Okay, what am I doing for time? Oh, I'm so slow. All right. Yeah, okay. I just want to skip that stuff, and I want to talk real briefly about the fact that everything we've covered in metrics so far has been about classification. True positives, false positives, specificity, sensitivity. These are all classification measures. And there's more that we haven't talked about. Again, spend some time clicking on things in the docs. Okay? Regression is a lot simpler. Basically, people use one of three things to measure performance in regression. So the residual sum of squares itself is basically directly proportional to mean squared error, right? Take the residuals vector, square it, just sum that up. Or take that sum and find its mean by dividing by the number of data points, right? It's like literally a constant. Mean squared error, residual sum of squares. There's just divide by the number of data points between them, okay? Because one's an average and one's a sum. Okay, so very typically, people will use mean squared error or the sum of squares itself, both of which are basically the loss function that we're optimizing anyway for regression, for at least OLS regression. An alternative viewpoint is R squared. Who's got some super stats, wants to tell us what R squared typically is in a stats class? Anybody remember what R squared is in statistics? Or what R is in statistics to start with? You almost said it. The correlation coefficient, Pearson R, right? If you report the correlation of X and Y, right? The correlation coefficient, most people are reporting a statistic called Pearson R. There are multiple ways to calculate correlation. Pearson R is just one way to calculate correlation, just to be clear. But if you take R, a correlation coefficient, and square it, that's R squared. It's Pearson R squared, okay? So, correlation coefficients when the dots line up perfectly, right? If your scatter dots look like this, that's like an R value that might be, I don't know, like 0.75. So R squared is going to be 0.75 squared, which means that, because correlation coefficient like this is 1, right? Perfectly lined up. Okay? So that's R is 1. That means R squared is also equal to 1 when the dots are perfectly in line. Or in other words, when your line of regression goes right through every frickin' dot, right? That's low error, baby. But if your line of regression, has got a lot of scatter around it, then your R squared is going lower. And if your dots are completely random with your line of regression, if this is a sphere of dots around it, then your R squared is 0, right? Okay, so when people say R squared, they're usually imagining, because they come from a statistics class, a number between 0 and 1, where numbers close to 1 mean the line of regression lies right on top of all the data points, and numbers close to 0 means the line of regression has no relationship to the dots. Okay? So, small change is that with scikit-learn, it reports an R squared that can go negative. And it's the equation that's right here on the screen. Don't worry yourself too much about it. It's an alternative formulation of R squared that doesn't involve Pearson correlation, but it matches Pearson correlation definition between 0 and 1. Okay? So anywhere between 0 and 1, this matches the Pearson R squared. What does it mean when R squared goes negative when scikit-learn uses R squared as a metric? It means that you would do better in this case, instead of putting the line of regression in where we have this absolutely random dots, you would do better to guess the average Y value. The average Y value will produce a lower error than your actual line of regression. Okay. Anytime that's true, this R squared metric will go negative. Okay. So other than R squared, which is about a goodness of fit, right? And just a reminder, another way R squared is talked about in statistics literature is variance explained. So just to think about this as variance explained for a second. If I know the x coordinate of a data point, how much do I know about its y coordinate? Okay? So if I just say, okay, my x is 13, so if I look at these scatter dots, I'm just going to eyeball this. It means my y value is somewhere like in this range, probably. You know, if I was just going to draw more data points in this range, probably think that we'd probably see something around here. Okay? And if I'm looking at this case, where the line's right on there, if I know the x coordinate, it basically determines the y coordinate, right? With very little spread. And in this case over here that I was drawing, knowing the x coordinate tells me jack shit about what the y is, right? Because the y could be anywhere in here, and it wouldn't be any different at this x coordinate than it would be at this x coordinate. So R squared also can be talked about as variance explained. If R squared is 0.75, it means that knowing the x coordinate explains 75% of the variance in the y coordinate. Okay? And if R squared is 0, well, you know what that means. Yeah?
Why did you square the R value?
Yeah, so Pearson correlation coefficient R squared is the variance explained. That's how you get it to be the percent variance explained, okay? And that's the classic statistics definition, is percent variance explained. I'm not enough of a statistician to be able to explain it better than that. I'm sorry. Okay, one other thing to point out. I talked about mean squared error. I talked about R squared. If you don't care about the squared error, you can use the absolute error. Mean squared error or mean absolute error. Just like with a loss function that's an L2 style on the residuals or an L1 style on the residuals, right? What do I care about? I pick squares when I care about that single outlier data point. When any really bad error is really bad, I would pick mean squared error as a metric. I would pick an L2 loss function. When I don't care, if I'm okay with like one really, really bad data prediction, but I want on average most of my stuff to be better, then using the mean absolute error discounts that big outlier, right? That big outlier doesn't have as much influence. And so if I care more about the average, most common predictions, then a mean absolute error can be useful, just the same way that an L1 loss function is useful to optimize for that. Okay? All right, I made it through my stupid things. I had 0 time to go through this metrics notebook, but you should. So, see you next time. Hey.
This might be too early, but like I don't want to